NASA's Voyager 2 spacecraft has been sent back its first message from interstellar space.
In 1977, two spacecraft launched from Earth, carrying a golden message from humanity. Voyager 1 and Voyager 2 were twin emissaries of knowledge and exploration, destined to travel farther than anything humans had ever built. At first, they were simply tasked with a grand tour of the outer planets. But what they delivered, decades later, was something far more profound, something many overlooked. While the world marveled at Saturn's rings and Jupiter's storms, something slipped past public attention. For years, it remained buried in data archives and overlooked by headlines. Now, it's becoming clear. Voyager delivered a message that could reshape how we view the universe and ourselves. Voyager 1 lifted off on September 5, 1977, just days after Voyager 2, with a mission to explore Jupiter and Saturn, later extending into a journey beyond the edge of our solar system. Carrying a golden record filled with Earth's sounds and greetings, it symbolized humanity's hopes and curiosity. But while most people focused on the planetary images and technical milestones, Voyager was quietly collecting data that no other spacecraft had ever obtained. Data from the very edge of the solar system, where our sun's influence ends and interstellar space begins. For decades, Voyager 1 traveled silently through the void, gradually moving beyond the influence of the solar wind, the stream of charged particles flowing from the sun. In 2012, something remarkable happened. Voyager 1 crossed the heliopause, the boundary where the solar wind is stopped by the interstellar medium. It became the first human-made object to enter interstellar space. But it wasn't just the milestone that mattered, it was what Voyager found there. Everyone expected a gradual transition, a thinning of solar influence. But what Voyager detected was a sharp boundary, like stepping through an invisible curtain. On one side, the solar wind dominated. On the other, it vanished. Magnetic fields, cosmic rays, and particle densities shifted dramatically. Voyager's instruments recorded a sudden jump in high-energy particles and a strange consistency in the interstellar magnetic field. This wasn't what scientists predicted. It suggested that the structure of our solar system's boundary was far more complex and possibly even shaped by forces we didn't fully understand. For years, these findings were downplayed, buried in scientific journals, discussed at conferences, but barely mentioned in public discourse. Meanwhile, Voyager 2 followed its sibling into interstellar space in 2018, confirming many of the strange observations. The boundary was again unexpectedly sharp, the changes abrupt. But there were differences too. Voyager 2's instruments still functioned better than Voyager 1's, especially its plasma sensor, allowing even more detailed measurements. It became clear. The heliopause was not uniform. It was dynamic, perhaps even rippling or fluctuating over time. What does this mean for us on Earth? The implications are deeper than they appear. For one, Voyager revealed that the protective bubble around our solar system, formed by the solar wind, is far more fragile than we thought. The interstellar medium outside is filled with cosmic radiation, and this radiation is held back only by the strength of the heliosphere. If the sun weakens, or if we pass through denser interstellar clouds, Earth could be exposed to higher radiation levels. This has consequences for climate, biology, and even space travel, but that's only the beginning. One of the most startling discoveries from Voyager's journey beyond the solar system is the presence of low-frequency electromagnetic waves, essentially plasma waves, emanating through space. In 2013, scientists detected a strange, eerie sound in Voyager 1's plasma wave data. It was unlike anything heard before, a rising tone, like the whine of distant machinery. This was the sound of interstellar space itself, and it showed that even in the void, the universe is alive with invisible vibrations. These plasma waves revealed something stunning. Interstellar space wasn't empty. It was dense with charged particles, flowing fields, and dynamic structures. The data suggested that the interstellar medium isn't just a passive region of space. It's active, interacting with the heliosphere and possibly shaping the environments of other star systems too. Voyager gave us a glimpse into how stars might be connected by a web of energetic material, and how our own solar system might be just one cell in a vast galactic organism. Even more mysterious were the deviations in magnetic field direction recorded by Voyager. The expectation was that the magnetic field of the Milky Way would dominate past the heliopause, aligning smoothly with interstellar space. But Voyager 1 detected a different orientation than predicted. Some suggested that local interstellar magnetic fields were twisted, or that hidden structures were distorting them. Others proposed that Voyager had entered a magnetic void, or an area where galactic fields curl strangely. For years, this anomaly puzzled scientists, and many simply moved on. But recently, attention has returned to this overlooked data, and new models are being proposed that could change how we understand magnetic environments in space. Another overlooked revelation came from the Golden Record itself. Designed by Carl Sagan's team, the record contains greetings in 55 languages, music from across cultures, and images representing life on Earth. It was intended as a message to extraterrestrial civilizations. For decades, people dismissed it as symbolic, more artistic than scientific. But Voyager's distance now raises an important question. What if it's not just a message, but a probe? As Voyager continues its silent journey through interstellar space, it's becoming a test case for long-term contact. It may never be recovered or intercepted, but it carries with it humanity's fingerprint, evidence that we reached beyond our planet. The Golden Record's very presence on an interstellar path means that, even accidentally, we have sent a signal into the cosmos. If some other civilization is out there, even centuries from now, Voyager may be the first introduction they get to humankind. As Voyager drifts farther from Earth, its power supply dwindles. The plutonium-238 in its radioisotope thermoelectric generators is decaying. One by one, systems are shutting down. Cameras are long since off. Communication grows fainter each year. By 2030, both Voyagers are expected to go silent forever. But the spacecraft themselves will continue traveling, undisturbed, perhaps for billions of years. Long after Earth is gone, Voyager will remain, a tiny, silent ambassador of a long-lost civilization. The most shocking aspect of the Voyager mission isn't what we've seen, but what we might have missed. In its raw data are unexplored patterns, unsolved anomalies, and hints of phenomena we don't yet understand. Some researchers believe Voyager has already detected clues to structures in the interstellar medium that could change astrophysics entirely. One theory gaining attention involves the possibility of filament-like currents flowing between stars, subtle traces of plasma highways that link stellar systems. If true, this could hint at an interconnected galactic environment, something beyond our current understanding of cosmic isolation. The more we study the data, the more we begin to suspect that space is not just a void, but a medium, like an ocean with currents, turbulence, and waves. Voyager may have detected subtle changes in pressure and density that hint at larger, flowing structures. The solar system might be traveling through a region of space unlike any we've seen before. It raises questions that scientists are only beginning to ask. Could interstellar weather affect Earth? Are we moving into a different region of the galaxy with properties that influence cosmic radiation or magnetic behavior? Voyager's journey also challenged how we think about time and legacy. When the spacecraft launched, many of the people who worked on the mission were young engineers. Today, they are either retired or no longer living. The project spans generations. Each new piece of data is a baton passed forward in time, a message from the past to the future. And yet, some of the most profound insights are just now being unearthed from decades-old transmissions. As modern data tools and AI-based analysis are applied to Voyager's archive, strange patterns are emerging, subtle changes in particle flows, unexplained blips in sensor readings, and trends that weren't visible until now. NASA scientists recently reanalyzed data from both spacecraft and found curious discrepancies between what Voyager 1 and Voyager 2 recorded at the heliopause. The energy levels, particle composition, and field orientation were unexpectedly different, even though the two spacecraft exited the solar system only a few years and a few billion kilometers apart. This suggests the boundary is more than just a line. It's a living, fluctuating zone. Something dynamic is shaping our solar system's edge, and we're just beginning to understand it. Then there's the mystery of the termination shock, the region where the solar wind slows down dramatically before being stopped completely at the heliopause. Voyager crossed this zone and recorded odd behaviors. Instead of a clean, steady decrease in solar wind speed, it found turbulence and layering. Some scientists think this may be due to shock waves from solar events colliding with the interstellar medium. Others believe it could be a sign of unknown physics at work, a mismatch between what we expect from particle models and what's actually happening out there. Even the way the spacecraft communicate is astonishing. Each Voyager transmits a weak radio signal, equivalent to the power of a refrigerator light bulb, across billions of kilometers of space. The signal takes over 22 hours to reach Earth, traveling at the speed of light. Yet from that signal, scientists can determine the spacecraft's position, trajectory, and environmental readings. The data rate is extremely slow, measured in bits per second, but it contains some of the most valuable information we've ever gathered. And inside that signal, more secrets may lie. Some researchers believe that patterns in the plasma wave recordings could contain hints about gravitational interactions, or even unknown particles in the interstellar medium. Others suspect that Voyager may have already encountered anomalies, subtle deviations in expected measurements, that point toward the presence of dark matter structures or unexplored cosmic forces. While this remains speculative, the sheer uniqueness of the data makes Voyager one of our most important cosmic laboratories. The spacecraft also changed how we understand space exploration itself. It proved that a small, durable probe can survive for decades in the harshest conditions, far beyond the original mission parameters. This has inspired modern missions like the Interstellar Probe Project, still in early development, which aims to go even farther than Voyager, with updated technology to map the outer heliosphere in detail. Voyager showed us it's possible. More importantly, it gave us a reason to try. There's also an emotional element that can't be ignored. Voyager represents humanity's first physical step into the galaxy. We've sent rovers to Mars, probes to the gas giants, and landers to asteroids. But Voyager is different. It isn't orbiting or stationed anywhere. It's escaping. It's on a one-way journey through the stars, untethered to any planetary system. It will not return. It drifts through the galactic dark, carrying the essence of our species, our music, our greetings, our story. Carl Sagan once said, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space." He acknowledged that this was unlikely, but not impossible. And that sliver of possibility is what makes Voyager so profound. It's not just data and metal, it's hope. It's a statement that we existed, that we tried to understand the universe, and that we cared enough to say hello to the unknown. As of now, Voyager 1 is over 15 billion miles from Earth, the farthest any human object has ever traveled. Voyager 2 trails not far behind. They are in different parts of the sky, sending their fading messages back to Earth, each pulse taking almost a day to arrive. They are time machines in reverse, not showing us the past, but sending the present into the future. Long after their batteries fail, they will continue to coast among the stars, monuments of human curiosity. But here's the strange part. Despite all they've done, Voyager's most important contribution might still be waiting in the data we haven't understood yet. Hundreds of gigabytes of scientific information have been transmitted over the decades. Some of it has been analyzed, but vast portions remain untouched or only partially interpreted. In an era of advanced machine learning and AI, researchers are now applying new tools to old data and uncovering patterns never seen before. This includes subtle frequency shifts in plasma waves, irregular timing and magnetic fluctuations, and unusual particle interactions. Some of these could be instrumental artifacts. Others might hint at phenomena that fall outside our current models. Scientists are asking questions they never thought to ask 20 years ago. What if Voyager picked up traces of dark energy interactions? What if the interstellar medium itself has structures we've never imagined? Giant waves, magnetic tunnels, or ancient remnants of supernovae that leave invisible fingerprints. More speculative still is the idea that Voyager might encounter interstellar dust or debris from other civilizations, long-dead remnants or non-natural objects. So far, there's no evidence of this, but it hasn't stopped some researchers from wondering. If anything unusual appears in the data, we now have tools that can detect the subtle difference between natural and artificial patterns. And if we ever do find something unmistakably non-natural, it will likely be Voyager that found it first. As its signal grows weaker, every bit of data becomes more precious. NASA engineers have begun shutting down instruments to conserve power, first the ultraviolet spectrometer, then others. Eventually, the spacecraft will fall silent, but even then, they will continue their mission, one that doesn't require power or communication. Their new task is simple: to drift, to wander, to carry the story of Earth into the dark. In a way, Voyager isn't just a scientific mission. It's a philosophical one. It's a question, launched into space. What happens when we reach beyond the limits of our world? What will we find, not just out there, but in ourselves? For decades, everyone focused on the headlines: pictures of Saturn's rings, the great red spot, the pale blue dot. But the real story was hiding in the numbers, in the frequencies, in the fields and waves beyond our sun's reach. Voyager delivered something we all ignored for years, a message not just from Earth to the stars, but from the cosmos back to us. A message that says the universe is deeper, stranger, and more alive than we ever imagined. And now, as Voyager enters its final chapter, NASA and the world are beginning to listen.